And I am going to pull up underneath our camera the problem so that we can look at them, and then you can let me know what you're interested in seeing. So I'm going to go underneath my camera, and the first problem that's assigned is problem 2.1. Let me zoom in here. Now, as we had identified the last time we were together, problem 2.1 is just like that first, I think it's like sample problem or concept application 2.3, where we've got two forces and we want to find the resultant using the sine and the cosine laws. For the first three problems here in this problem set, numbers 2.1, 2.5, and 2.7, we're using the trigonometry, if you would, the sine and the cosine laws, not the rectangular component method. All right. I know we learned the rectangular component method. I know a lot of people like that better, but for these first three, we're like just recalling that stuff and exercising our muscles. Going forward, most of the time we're going to be using the rectangular component method, but it's important to be able to do it both ways. Okay. So on this very first one, you're going to sketch it out. And then you're going to solve for the resultant, and it's going to take that same process and formatting as we did in that, I think it was 2.3, one of the first application problems that we did in the resultant section. So what I want to ask is, does anybody have any questions setting this up or looking at it or wondering how to approach it at all? Okay, now remember, when you're doing these couple things, number one, you have to have a good diagram. You're going to draw that diagram graphically, like the parallelogram method or the triangle method, and then you're going to be solving for what they're asking. Make sure you make it big enough. Make sure that you have labels and arrowheads on everything so that when you add that, it's clear and easy for me to read. Okay, and again, going back to the practice problems, the one that we did in class, the ones that you hand in, for this module, that's the process and the formatting that I require, okay? Don't go off on your own. Do it the way that I'm asking you to, all right? Because then all the elements are there, and then they're easy to read for me, for one, but they're also easy to go back to, and you've got all the steps that you can, easily reference if needed, okay? So nothing 2.1, any takers at all, setting this one up. That's usually, it's all in the setup for like these first three problems, making sure you've got your angles correct and that kind of thing. Okay. So then the next problem, nobody has any questions here. This one is 2.5. 2.5 is like the barge problem that we had, except the barge was horizontal, okay? This one is just vertical, but again, same process. We have a resultant that's going to be vertical, and we want to find the magnitude of the resultant, but also the magnitude of P, okay? In this one, if I'm remembering correctly, you don't need the cosine law, you just need the sine law, because you'll know what all the internal angles are, which is kind of nice, okay? Are there any questions on either setup, sketch, approach, requirements on 2.5? Again, just like that barge problem in the chapter that we did for practice problems. Okay, all right. I'm gonna peek at our chat, just make sure, okay. Kind of watch this as well, so you guys can always put it in the chat or let me know verbally. The next problem that we had assigned, oopsie, not 27, I need 7, where's 7? There it is. The next problem we have is this one right here. This is it's a trolley wheel, and it has two forces that are acting on it at point A. We have 1600 newtons at that 15-degree angle, and then we've got P at alpha. Alpha is given up in the problem as 25, and it's really the very same problem as the previous one. In this case, we have our resultant that's going to be vertical, and we need to calculate what P is going to be and what that resultant is, okay, based on the information that you have here. So again, sketch it out, put all your labels in place, and then show the process of solving for it using, I think the sine law is the only one that you need here. I think the cosine law is only for that very first one, if I remember correctly. Okay, but the key is the setup. So is there anyone who would like to see how to kind of formulate and put all the angles in place for each one of these? Okay. If not, I don't want to waste anybody's time. Good. Okay, that's awesome. So so those are the first three. Then the next ones that we're looking at, I think if I remember correctly, I better go back over here. Yeah, 18, 19, and 22, 26, 27. So 18 and 19. All these papers here. There we go. It's nice that they're loose leaves, but yet they get out of order really easily. Okay, now I want to remind you that the last time we were together, we did a problem where we went from a series of forces, we broke them into their components, we found their resultant by what we called the rectangular component method, okay? So the first part here for number 18 is number one, breaking these forces into their X and Y components, all right? So what you'll do is you'll show one X and Y axis with all three of these forces on. You're gonna show the angles, you're gonna have the labels, each one of them is going to have an arrowhead. And then you're gonna have your X and Y's identified. Then you're going to, for number 18 and for number 19, so for this one and this one, you're going to determine the components. So you're gonna calculate each one of the components, okay? Then for number 18, correspondingly, on the following page, on 26 here, determine the resultant of those three forces. So now you're going to take it that next step further where you're going to sum the forces in the X to get the resultant X component. Okay. And based on the direction, left, right, up, down, you're going to have a positive or a negative. Okay. And then you're going to do the same thing on the Y axis, sum the forces in the Y to get the resultant Y component. And then you're going to use those two to determine the resultant. Now, we only did one practice problem on that. That was the last practice problem we did when we were together last time, okay, which was enough, right? We were kind of like, okay, we've got a lot. So that's that process. But this evening, I'm going to work 18 and 26 together. So you get another process under your belt as well as get done with one of those homework problems, okay? So even if you don't say you have a question on it tonight, we're going over it, okay? But 19 will be that exact same process. 19, and then its partner is number 27 on the next page here, where you're going to find the resultant of those forces in number 19. Okay, so we'll do 18 so that you've got another good process, a second good process in requirements, and then you'll do number 19 in that similar fashion, but different numbers. Okay, so that's a plan. But then we've got number 22. Okay, number 22, here we're looking at this cable. Now, in this case, the answer is not in the back of the book, but I do have the answer, on our application problems. And in this case, there's a cable AC and exerts a force on beam AB. Now, they don't show the force on here. So this force is actually acting with its tail at A, and it's pointing up and to the right along that cable because it's supporting. It's like pulling on the beam so that it doesn't fall down. And it tells us that there is a vertical component to that force. So this is force P right here. P is along that cable and its vertical component, so we would call this PY, would be 350 pounds. And using the information we have some angles and such, we want to find out what is the tension in that cable, or what is P, its magnitude. And then also, what is the horizontal component? So this would be PX right there, pointing to the right with that information. So it's really another little bit different approach at the components of a force, right? So that's number 22. And then our last problem in this kind of portion here is number 31. And we'll look at that after we look at 18, okay? 18 and 26. So if you have already done 18, that's awesome. But if you haven't, then now's a great time to kind of follow along with me. And we're going to be going through and taking this step by step, making sure we've got good process for problem 2.18 and 2.26, okay? How many have done this problem already? Okay, a couple of you, not all of you. All right. So then as you're kind of looking at it, just keep yours, kind of at hand. Make sure you've done the very same things in the same way that I asked you to in the practice problem. But it's a good check to be sure you have all the elements that are needed. Okay. So as we look at number 18, then the first thing we need to do is draw a diagram. Now I'm going to grab out a straight edge. As you know, I kind of make my diagrams pretty big, but I find it helpful. Oh, I grabbed it back over here. I find it helpful because that way I can add the labels and information as I go along. So I literally am going to take like the top third, almost the top half of my piece of paper to draw this diagram. So I'm going to have a nice big X and Y axis. Okay. And again, it's just so that I have the ability to add all my information and be able to show it and label the way we need to. Okay. Now I have a protractor, so I might as well, you know, try to get my angles in here. You don't need a protractor. You can just kind of eyeball it. This is about 25 degrees. And this is going to be 60 newtons long. Now I'm not going to measure or 60 pounds. I'm not going to measure the length, but proportionally, if we know that some of these are longer or shorter, and I'm also going to call this force A. Okay, I'm just going to call it A. That way, when I have a force, you want to give it a variable, because then when I do these components, I can have an AX, an AY, and so on. Okay. And then I know that this is at 25 degrees. This is my Y-axis. This is my X. Then I'm going to do my 40-pound force. So I've got, or 40 pounds. So then I'm at 60 degrees. So that's going to be here. So I want to make this shorter than my 60. So maybe right about there. So this I'm calling force B is equal to 40 pounds. Okay. And then this angle is 60 degrees. And then the last one that I have is going to be C. And this is 50 from the vertical. So 10, 20, 30, 40, 50. And this one is 50 pounds. So a little bit longer than the last one. Go there-ish. This is C. It's going to be 50 pounds. And this angle is going to be 50 degrees. Okay. Now that I have each one of these drawn in here, so again, don't try to make this super small, because now when I add my components, it's going to start to get really busy. Okay. So to add each one of my components, I'm going to have components for any force that does not land on the X or Y axis. Okay. So I'm going to start with my A. This does not land on the X or Y axis. It's, you know, tipped up from it 25 degrees. So the first thing I'm going to do is I'm going to draw my little lines down and over. These are parallel to the opposite axis. Where they intersect with the X and Y axis is going to be where I'm going to set the arrowhead for the corresponding vector. So remember, we don't float X and Y components out here at the dashed lines. Their point of application is going to be on the X and Y axes. Okay. So I am going to offset just a little bit higher here for my top one. So this is going to be AX. Okay. And you want to label it. And then this is going to be AY. And label it. It needs an arrowhead and it needs a label. I should see an AX and an AY, because you'll be solving for an AX and an AY. And then I'm going to do the same thing for my B force. I'm going to go over and up and then offset from there so I can see it, and an arrowhead. See, I'm getting close. This is going to be my BX, arrowhead on there, and then BY is going to point down right here. This is going to be my BY. And then lastly, I'm going to do this very same thing for C. I'm going to go over and up and whoops, point here. It's going to be CX going to the left and CY going down. Okay. So you can see here, I can clearly see that I've gone from 3 forces to 6 forces. okay? And each one has a label. Now, at this point, if there's any angles to solve for, anything like that, you're going to want to do that. But we were given all of the angles. So the next thing to do is, and this is part of problem number 18, this is going to be solving for the magnitude of each one of the components, okay? So if I call this, I'm going to call this step number 1. This would be my diagram, okay? And then step number 2 is going to be components, okay? So I'm going to start with A, go to B, and then C, just because of alphabetical order. So I'm going to look at the angle that I'm given. So you'll notice here that I've got 25 degrees. I need to find, I'm going to start with the X, the AX component, knowing the hypotenuse. So as we look here, this would utilize the cosine function, right? The side adjacent is what I'm trying to find. And I have an angle and the hypotenuse. So I would write this out as AX is equal to the cosine of 25 degrees times 60 pounds. Make sure that you have your units in all phases of the problem. If you leave this at 60 with no units, you get a point off each time it happens. Then you owe me points sometimes. Maybe not that, but you will get points off. It's really important that we put them in there. We're setting the precedence of starting to put the units in now early, because as these formulas get more complex or we're doing different things, not only in this class, but other classes, you start to get in that rhythm, and the units that you end up with will let you know if you set up the problem correctly. Okay, so it's really important. So make sure you have your units in here. And then what we're going to do is simply multiply this out. We're going to find 25 cosine times 60. My AX is going to be equal to 54.38 pounds. Now I'm going to hold an extra decimal place here just because it's inside of the problem, because I'm going to be using this. So then I'm going to do my Y component. As I look at my Y component, its equivalent length is opposite, but it is not out here. Do not label out here AX or AY. Don't do it. Resist the urge. Okay. AY is on the Y axis, and it has its vector, or its vector over there with an arrowhead. So because it's the side opposite, and I'm going to use the hypotenuse, AY is going to be equal to the sine of 25 degrees times that 60 pounds. Again, put your units in here. Don't leave it at 60. And then AY is equal to 25 sine times 60. And it's going to be 25.36 pounds. Okay. So go ahead and find your components for B and C. Okay. Do not put the negatives on these. Just put the absolute value. Our positive and negative will come when we do our adding and subtracting of the vectors in the next step. Okay. So just magnitude. Now, once we have our components, you can compare to what I have here or check the answer key. The answer key is going to have positives and negatives, so you know if they're pointing in the right direction. But here I just have my absolute values, and I'm going to put my positives and negatives in the second step. Now, after you have your components all done here, X's and Y's for each one of those, you're done with problem number 18, if you would. That's problem 18. That's the first part of this, okay? So now we'll be moving, actually, before we move into that, are there any questions? Everybody got the components here? Make sense? Or just double check my work because I'm doing it along with you, right? Okay. So now we're ready to start looking at the resultant. So problem number 26 wants us to find the resultant of these three. So what is the one force that would replace all three of these separate forces, now 6 actually, and they would have it would have the same net effect on the body, okay? So I'm gonna actually kind of pull this out here, and I am going to look at my diagram like this, and I'm gonna kind of right below it. Okay, so the very next thing that I'm gonna look at here is I need to, and this is step number 3, I need to find the Rx, which is the resultant X component, and the Ry. Okay, I want to know what the resultant is along that X-axis and the Y-axis. So since I have all of my components now aligned horizontally and vertically, I'm going to focus on each one of those directions to determine, okay, what's the net value of what's going on there. So we're going to start by looking at our horizontal axis. Now, before we do, we have to define what we call our convention. That convention is going to tell us what's positive and negative. So if you remember, we can't forget to put our convention at the top of our problem, and it tells us what is positive and negative. If you forget the convention at the top of your problem on any one of these where we're using positives and negatives left, right, up, down, which is pretty much everything, points come off. Okay, you got to tell me what it is. This is important. All right, so now going forward with this next step, anything that I have a positive in front of, I know that it's pointing to the right. Because remember, these are all vectors we're dealing with. The sign gives us the direction. And this tells us then how to interpret the sign. We are going to always use this convention, but you need to put it at the top of each one. Because you could change, in theory, you could change the convention. If I was dealing with a lot of forces going down, rather than having negatives for everything, I could say, oh, all the forces going down are going to be positive. And that's how my convention is. And I would identify this at the beginning of a problem. Okay. So that's why we need to identify it. We need to live by it, if you would. So now we're going to find those. And as we did last time, we're going to sum the forces in the X direction. So write it out. This capital sigma, this is a Greek symbol, summation of the forces in the X, capital F sub X. You have to write that. Don't do summation of X. Don't do summation of force. Don't do Fx. You have to put the summation of capital F, that's the forces in the X direction. This is like common of how we write this, is going to be equal to the Rx. So whatever we come up with, the total summation of the forces along that X-axis, that's going to be our resultant X component. Okay. Now we're going to perform it. So this is what I call showing me what you're going to do, the equation in variable form. All right, this kind of announces what you're going to do, and now we're going to do it down below. So we're going to set up the equal sign here, and I'm going to go back to, this is why I got my diagram. I'm going to go back to this diagram, and I'm going to look just at the horizontal axis, my X-axis. I'm summing my forces along the X-axis, and here's where the convention comes into play. You're going to notice that I have AX and BX going to the right. Those are positive values. So I'm going to have in my equation, I'm going to have a positive AX and a positive BX because they're going to the right. So the positive out front, I know that they're going that way. These are vector quantities, okay? And then you're going to notice I have one other force along the X-axis, and that's the CX. And that CX is pointing to the left. So then I'm going to go minus CX, and that's what the minus does. I'm pointing to the left. So these values come from the convention. These values come from the convention. So list when you do your components, just just the absolute values. I don't need to know positive, negative, up, down at that point. It's going to come in right here, okay? And based on your convention. All right, now we're going to put our values in. So now we're going to look back at those components that we just created, okay? We're going to look down this X column. I always kind of put them in the same columns. So I've got AX is equal to 54.38. So I'm going to put that in there, 54.38 plus 20. Oops, what did I forget? I forgot my units. So I'm going to erase and I'm going to add them in there. I'm going to use the symbol for pounds, 20 pounds. And then I'm going to have minus 38.3 pounds. So make sure you put your units in all phases of the problem. Here too, if you forget to put pounds, 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 you could also do LB, LB, LB. It's totally fine. I just find LBs for me look like, the L looks like ones sometimes. And then if it's at the end of something, then I don't want to inadvertently stick a 1 in there. So I usually use the symbol in my equations. So I've got my units there. And now they all have the same units or the variable. I can add and subtract these algebraically. So I should get 0.38, 20 plus minus. So you should come up with Rx is equal to 36.08 pounds. Did you guys get that? All right, this is not a final answer, so no box yet, but remember the magnitude is a 36.08. The direction is the positive value. If I would have gotten a negative here, it would just mean I'm pointing in the opposite direction. But I've got a positive, so I'm going to the right because I know that because of this convention. Okay, so you have to have this at the beginning of your problems. All right, any questions so far? For those who did it in good shape here, awesome. All right, now we're going to do the same thing for our vertical axis. So we're going to say, all right, sum our forces in the y direction equal to Ry. So you're announcing, you're telling me what you're going to do, and now we're going to do it. All right, and this is the way you write it, the only way you write it. Now we're going to look back at our diagram, and we're going to look only at those vertical forces. Okay, so we're gonna see. Okay, we've got a positive AY. It's going up, right? So I'm going to put a positive AY. And then I've got a negative BY and a negative CY because those are going down according to my convention. So negative BY, negative CY. Okay. And now I'm going to put the numbers in. I have to skip a row because I have the little tails on the Y's. So here are my values in the second column for my components. So I'm going to have a 25.36, sorry, pounds minus 34.64 pounds minus 32.14 pounds. And again, the values or the signs, the positives and negatives come from our convention and identifying up, down. In this case, up is positive, down is negative. Right. So now we can say Ry is equal to, and we're going to add and subtract that algebraically. Now, again, I want to reiterate, yes, this is usually the preferred method for doing the resultant, but remember those first 3 problems are doing sine, cosine law, and then the rest is going to be this when there's a resultant needed. So this one, we're going to have a negative 41.42 pounds, and I'm holding an extra decimal or so inside of my problem so that I have a more accurate result at the end. Okay, any questions at this point? Everybody kind of with me? So now what we've done is we've combined what's on the X and Y axes, and now we've gotten it down to, okay, on the X axis, what is the resultant or the one force that would have the same net effect in the X direction? The same thing for the Y now too. Okay, so let's go ahead and draw these two. So our step number 4 here is I'm getting ready to calculate my resultant, my full resultant, capital R. All right, now, before I draw it out, I want you to make a diagram with Rx and Ry as you would interpret its direction. Okay, so you're going to have an X and a Y axis, and you're going to draw RX and RY. And we'll see if we agree. Which quadrant are you in? Fourth quadrant, right. We've got a positive x-axis, or I'm sorry, a positive x-directed Rx, right? So we're going to draw that right along the x-axis. We're going to say Rx is equal to 36.08 pounds. Okay. And then we've got our RY negative. The negative just says I'm pointing down. Okay. So when you draw this, you're going to draw it going down, the arrowhead along the y-axis, kind of in proportion. They're very close in size. This is going to be RY is equal to, now, do not put the negative in front of the 41. Why not? Go ahead. It's a vector, and why wouldn't I put the negative in front? The arrowhead tells me. I've got the arrowhead drawn, so don't put a negative in front of the 41 now. So 41.42 pounds, and the direction going down is the negative. If you would put another negative in here, it's kind of like, it's not right. It is redundant, and it could be interpreted, incorrectly. Okay, so now that you can see I've got the components of my resultant. So what I'm going to do is through the endpoint of each one of these that I drew, okay, just going to draw kind of construction lines, and where I find an intersection, the tail of my resultant is going to start back at my origin, and the tip is going to go to the intersection that I just created. Okay, so this is my resultant. So label it capital R. So you need to have arrowheads on all three of these vectors. You need to have them labeled Rx, Ry, magnitude, and then you need to label R, because we're going to be solving for that, and its direction, we're going to do theta. So make sure you label where theta is, because when you solve for it, I need to see an R and a theta in your diagram. So you have to draw this. Okay, so now we need to determine the magnitude of our resultant. Now, as we look at our resultant, you'll notice that it's the hypotenuse of a right triangle, right? And we know the two legs. So what right triangle function would we be able to use to determine what the resultant is? Go ahead. Go ahead. Anyone? Nope. I don't know an angle yet. I want to know what the resultant is, the magnitude of the resultant. No, I'm not going to lose the law of cosines. I have a right triangle. Pythagorean's theorem, exactly. So I know the two legs. I can find the, you could use the law of cosines if you wanted to, but I'd much rather do Pythagorean's theorem because I'm a right triangle, right? So I am going to write out, let me see here. So if I do R is equal to the square root of Rx squared plus Ry squared, right? Everything under the radical there. So now I'm going to put my values in here. And I am going to be 36.08 pounds. Put your units in there, and you're going to square that quantity. Now, plus, you could put the negative 41.42 in here, but we're going to square a negative number, and what does it become? Positive anyway. So you can just put the absolute value in here. That would not be wrong. Kind of that recognition. And then make sure that you're fully under the radical. Okay, so you're going to square each one of these. You're going to add them together. And what is your resultant? You guys tell me what you got. 54.93. Okay. And it's pounds, correct. Yep. Now, how do we resolve the pounds? You squared the pounds in here right along with the value, right? And when we take the square root of the function, it comes back to just pounds instead of pounds squared. 54.93, is that confirmed? I don't have the answer in front of me. Okay, so that seems reasonable. Yeah. Okay, so we're going to put our box around here. This is the magnitude, right, of our vector. You don't have to put magnitude next to it. Am I done? What else do I need? I need direction, which is going to be theta, right? Now, somebody said tangent earlier. Now I can use tangent, right? Okay, so tangent theta is going to be equal to the side opposite, even though it's not out here, its equivalent is going to be our 41.42, don't put the negative pounds, divided by our side adjacent. It's going to be 36.08 pounds. Pounds cancel, put the units in there. And that's exactly what we want. We want this to be unitless. And then when we do our second function tan, we will get our value. I get 48.949 degrees, right? Now, I'll look at the answer key in just a little bit, but just so you know, any one of the answers that I give you guys is going to be from the back of the book. All right. Just because the book is really consistent with showing everything to 3 significant digits as its final value. So when you get your values, if you have an extra decimal or 2 and you're like, oh, I'm off, think back that theirs is rounded to 3 significant digits. And if you would round yours to 3 significant digits, would you have the same value? Okay, so that's what you're going to see probably as that difference. Like I said, hold a couple extra in your problem so that when you get to the end, round at the end, as opposed to too much rounding in the middle. Otherwise, as you know, then you're gonna inflate that as we go along. All right, so now am I done? I'm not, James. I thought I was. What are you thinking?
Well, you have your answer as 311 degrees.
Oh, well,
Have it from
I do. This is what I want here. The answer in there also, all I did was I went from 0 degrees all the way around so that I didn't have another way to say it. Does that make sense? So yes, just make sure that if you subtract this from 360, your number is right. But what I'm looking for is if you solve for theta, this is your number in this problem. Okay. Don't worry about that. That's really just your check. Does that make sense to everybody? You don't have to put it in that form. I just have the answer out there for you in that form so that you can know if your answer was right or not. This is what I'm looking for. Label that angle. Now, if you decided to label this angle and call it theta, and you did that same process, but it was 90 degrees minus 48.9, that's fine too. Okay. Just don't ever dimension it from another vector. Does that make sense? Always go from a standard XY, and most often it's going to be from the X. Okay. That's usually where you're going to see me do it and where things are referenced from. But if you do it from the Y, I'm okay with that too. Don't redo anything. If you did it from the Y, don't redo it. Just make sure that if you would have done it over here, it would have been 48, or if you subtract it from 90 degrees, you get that same answer. All right, so things to look for as you're handing in. This is the format. The book does more of a tabulated type of a thing, okay? Please don't do that. And the reason I don't want you to do that is because I want to get you used to using the convention. All right? And then identifying pluses and minuses here and writing an equation. When we start talking equilibrium in actually module 3, we're going to be writing equations of equilibrium, and we're going to be coming back to the same type of thing. So let's get in that practice of doing that now. Okay. So as we look here, number 1, diagram, nice and big so that you can have all of your labels, all of your angles, all of your vectors. Make sure you got them positioned in the right place. Components are on the X and Y axis. They're not floating out on the edges. Okay. So make sure that you're labeling and you've got arrowheads. Make sure you've got a convention. Put it in right at the beginning. Even for number 18, you don't necessarily need it for 18, but you're going to continue with problem number 26. So you're going to need it for that resultant. So make sure you have your convention up there. I'm looking for that. Okay. Then as we do our components, make sure that when you write these out, get your units in here. Okay. Because otherwise I don't want these units to magically appear at the end. All right. I want you to see how they're actually working out here. Okay, because then if they can combine with something or cancel, we want to do that work. All right. So don't magically appear at the end. Make sure that you have it in all phases of the problem. Then as we turn the page and we go over here, make sure that when you're finding your resultant X or your resultant X and resultant Y, you're going to sum the forces. This is telling me how I'm going to get that resultant X component. Okay, so you have to sum the forces in the X direction. You have to write it like this. Sum the X's, sum the F's. No. Sum the forces and then sub X, because that's the forces in the X direction, is equal to that resultant X component. And then now we're going to list horizontally positive and negative based on my convention, what I've got, and then I'm gonna put my values in with units and then combine, add and subtract as needed. Same thing for the Y. Once you have these two values, then you're going to use that to draw a diagram. Don't put this over here, okay? Draw a new diagram, have a new axis system, draw it in the right quadrant based on the values that you get for your X and your Y. And then label arrowheads, label the resultant, label the angle that you're going to calculate, and then you do that work for me and make sure that it's all consistent. Now, couple things. Why do we got to do it this way? Number one, this is going to be easier for you to go back and look at when we do our unit assessment. This is open book, open note. Okay. You're going to be able to look at it. Have you ever looked back at your own work and been like, what the heck was I thinking? What was I doing? Okay. This will help you to step by step work through it. Number two, it's easier for me to follow and I can see that you have everything there and I can get you feedback sooner. Okay. So that's why as well. Formatting is really important to me because as we look in here, I can't have you guys fill out just a quiz on Canvas and in multiple choice form and expect you to like know that you know statics. I need you to write it out. I need you to show me. I need to see the process. Okay. This is the foundation of like everything else in engineering. Okay. I need to know that you've got it. So yeah, I'm having you write it out right now. And you might say, isn't there an Excel spreadsheet? Yeah, there is. We can do an Excel, but this is really important work. Okay. So I need to be able to see what you're doing. I'm more interested in that process than in that final number because so many things can happen. You know, you can even like have the wrong number at the beginning, but if the rest of your process is perfect, you're getting 9 out of 10. All right. Or if I look at the very bottom and it was just a calculator issue where you maybe, hit a wrong number, but the whole rest of the thing was good. But if you just give me a final answer and I don't see any of the work and the answer is wrong, it's a 0, no matter how much right you did. Okay. So that's another reason. And then the third reason, I know it's really important. The third reason is going to be when you're out in industry and you're having to do some design work, you're going to do some of these calculations. It might not be all of them, but there'll be times when you've got to document how you came upon an answer or why you picked that bearing or why you have that size diameter on a shaft or why the gears that you chose are what they are. You got to show that process. So this is practicing doing exactly that. All right. So, so there's a couple different reasons to do it. So please practice this now, kind of get used to it early. And then all of a sudden you start thinking differently too, as you go through things. So, so just know that I'm not doing this to be a big pain in your tuchus. I'm doing it because there are really good reasons that are going to benefit you later on. All right. Okay. Any questions on what's required format or process wise? So we got done, if you didn't have this one done already, the with one of the homework problems. And if you did have it done, hopefully you checked your work as you went along and you have all the same elements that we have here that we talked about. Okay. Now I'm going to open it up to, are there any other questions that you have for the module 2 application problems up until 31, including 31? Are there any other ones that you want to see or you feel pretty good about them?
Set up 31.
I can show you how to set up 31s. So let's look at problem. Actually, you know what I'm going to do? I'm going to stop this recording here because then I'll call this 18 and 26 together and then we'll do a setup for number 31. So let me stop the recording and I'll be right back.